Hello, everyone. Mohammed Ahmed is a second-year PhD student at the Carnegie Mellon University, advised by Dr. Shah Rajat. His current research is focused on developing biological-inspired methods for making deep neural networks more robust to input perturbations, particularly adversarial attacks. In the past, he has worked on a variety of research topics, including machine learning privacy, neural model compression, and information retrieval. His work has been published in several conferences, including ICC, ICE-SSP, Interspeech, and ICPR. Ahmed, welcome to to give us a talk, biological inspired. For visions, filter improves the robustness to adversarial attack. Maybe you can explain more about what is for visions means. Yeah, please go ahead.
Okay. Hello, everyone. My talk is going to be about biologically inspired foveation filters and how they improve adversarial attack. I'll talk a bit about what foveation is, and it's something that we're probably all familiar with, but just not on this particular term. Anyways, I'll start off by introducing adversarial attacks, and then I'll move on to exactly what we're doing. So I think many people have already seen this photo in which the classical example of an adversarial attack in which you have a photo of a panda. Then you add a very small amount of noise to it to get the third photo, and then a neural network that was previously able to classify the first one as panda now classifies the third one as some other animal. And this is alarming, or this sounds very counterintuitive, because we as humans do not see any noticeable difference between the first and the third one, but from the perspective of the model, it's a very big difference, because it's classifying it as something other than a panda with very high confidence. So I'll talk a bit about how this comes about, why this happens. So the scenario that we have is that we have three entities. One is the ML classifier, one is the human, and then the third is the adversary. Now the job of the ML classifier is to replicate the human's decision function with regards to any task. So consider the example of image recognition, or let's say classifying animals. The model is given this image of a cat, if a human is given this image of a cat, they classify it as cat. And there's a region of, there's a class of images that is represented by this blue circle, all of which people would consider as cats. Now, what we want is we want to teach a machine learning model to replicate our decision function. So we want it to classify everything that we consider as a cat, and everything that we do not consider as a cat. We want the model to say it's not a cat. So to do this, we give the model a bunch of images and tell it, okay, these are images of cats. We do not provide any other additional information, whereas, so we are giving it very sparse feedback. Okay, and then we give it some other negative example, in this case, the image of a dog, and we tell it that, okay, this is not a cat. So we are giving it a very sparse information with just exemplars of different classes, and we expect the model to be able to classify these things accurately. Now, in contrast, human beings intuitively do it a little bit differently, because we have a very sophisticated notion of what it means to be a cat. It has 4 legs, it has certain types of ears, it is a certain size and such. There's a bit of science behind it, but we do not give this information to the model. We just give it a bunch of images, and we tell it to just learn to discriminate between cats and dogs in this case. Now, following the example I introduced earlier, we have 3 images of a cat. They live in this blue circle, which the humans consider to be cats, and then you have this other set of images of dogs that occupy this circle on the top right. Yeah, this one. And these are all images of a dog. And now the model is trying to learn a decision boundary that separates cats from dogs. Now, there are many, as you can see, there are many such decision boundaries that are possible that, given this training set, are equally good. Now it could learn this boundary, this boundary, any of these, because all of them do a perfect job on the training set. However, you may notice that in all these boundaries, there is this region in which humans would consider any image that lies here, humans would consider it to be a cat, but the model would classify it as a dog or as not a cat. And that is what makes adversarial attacks possible. Now, so the adversary, what it does is it searches for points close to images that cross this boundary while remaining within this blue circle. So to say another way, it tries to modify these images slightly so that they appear as the same semantic class, in this case cat to humans, but they cross the model's decision boundary. And that happens because the model is not perfectly modeling the decision boundary of humans, it's just it's modeling a decision boundary that is optimal for the training data. And in contrast, if there was a model that would learn this boundary, this one, that fully encapsulates the human's decision boundary, it would not be possible for an adversary to modify any image such that the human still calls it a cat while the model calls it a dog. Because for the adversary, to modify an image such that the classifier is going to start calling it a dog, this image, for example, would have to move over here. Now this area is the area for dogs. It's outside the blue circle that was the human's perceptual boundary of a cat, and therefore the adversary wouldn't necessarily have to modify it enough to actually make it a dog, or like make it so that it no longer looks like a cat to a human. And so this model would perhaps be adversarially robust because of the reasons I just described. Now there are several ways of computing these adversarial attacks. One of the earliest methods is called the fast gradient sign method. The idea is pretty simple. You take an image, you compute its gradient or the sign of its gradient, you scale that with some particular step size, which is epsilon. This is usually a very small number, usually 1 in terms of pixels, so that's 1 over 255, 2 over 255, up to maybe 8 over 255. But nevertheless, the noise that's added is imperceptible, and that just takes one single gradient step and pushes the image across the decision boundary of the classifier. So what this step essentially is doing is it is maximizing the classification loss with respect to the correct class y, which means it's basically trying to change it to an incorrect class. A slightly more sophisticated method is called projected gradient descent, in which the same principle is applied, but it's done in an iterative manner. So iteratively, for k iterations, the adversary is trying to maximize the classification loss. Keep in mind the word maximize, because generally we minimize the classification loss. When the classification loss is 0, that means that the data is being perfectly classified. When it's something very high, it means that nothing is being correctly classified. But okay, so the adversary is trying to iteratively maximize the classification loss, and at each step, what it does is it computes the gradient of the loss and then uses that to update a noise pattern that gets added to the image. So what it looks like is basically this. First, it uses the gradient, takes a step, then it applies a constraint. The constraint is shown by this term here. It's pi sub epsilon, and that constraint is that the perturbation has to be small. And what small usually means that it has to have a very small norm, usually in L infinity or a small L2 norm. So after it takes this step, it then projects the perturbation back into the constraint set. So if the step made the size of the perturbation larger than, let's say, epsilon in terms of its norm, it projects it back into so that it has norm at most epsilon. Then it takes another gradient step. Then it projects the input back to such that it has norm no more than epsilon. And this way, it can take multiple steps to find adversarial examples that lie within an epsilon norm of the original image. So now, the state-of-the-art methods that are used to make models more robust to such adversarial attacks essentially train the models to be robust. And what that means is they use a method called adversarial training. And the basic idea is that they train the model on adversarially perturbed images. So you can the algorithm is roughly this. For every example in the dataset, we compute an adversarially perturbed version using the same method that I just described, predicted gradient descent, and then we train the model on this adversarially perturbed data instead of the clean data. And you're essentially teaching the model to be robust to adversarial attacks. But a shortcoming of this approach is that essentially you are giving the model the test before it takes the test, essentially. It's because the algorithms used to compute attacks in the testing, in the evaluation phase, are the same algorithms that are used while training the model. So you're essentially training the model on similar perturbations, similar attacks as you are going to be evaluating them on. And the result is that they tend to overfit. So if a different attack methodology is applied, sometimes this adversarial training approach tends not to give good results on new adversarial attack generation methods. Now, for example, I've shown here several different types of corruptions that can be added to the model. So this is the projected gradient descent adversarial attack I just talked about. There's another type of adversarial attack in which a small patch is added to the image. There are other attacks in which real patches or like patterns are printed out in real world, and then they're used to attack the models in real life scenarios. These patterns look very different from this one, and this one looks very different from this one. And to humans, none of these are adversarial. To us, we as humans, we can correctly classify all these images, we have no problem. But if we conduct adversarial training using this method, it will only be robust to this method, this type of attack. It would be very less robust to this one or this one. And similarly to these ones, these are not adversarial corruptions, they're just common corruptions like blurring, noise, compression artifacts, etc. So ideally we want models to be invariant to all of these types of corruptions, but current defense methods would require us to train on all of them. However, in contrast, humans are invariant to all of these types of perturbations or corruptions without any specialized training on either of them. We have probably never seen such images with this type of patch added to it, but still this patch is not fooling us in any way. So that leads us to the hypothesis that perhaps the robustness of human vision is emergent and not learned. We have not learned specifically to be robust to certain types of perturbation, but rather how our vision or our visual system is organized or how it's constructed endows us with this type of robustness. And perhaps that's due to the fact that there are certain mechanisms and constraints that we as humans or generally animals have in their vision, but DNNs do not. So for one, the activation of biological neurons are stochastic, whereas the activations of artificial neurons in deep neural networks are deterministic. Secondly, the neural networking inside animal brains is highly recurrent. You have feed-forward connections, you have feedback connections that go from higher to lower areas. You have lateral connections that neurons in a particular area are all wired together. In contrast, in DNNs, we usually have exclusively feed-forward connectivity. That neurons from one layer only connect to neurons in the next layer. You don't have neurons in layer 2 going back to layer 1. You also don't have neurons in layer 1 communicating with each other, which is very different from how it's organized in animals. Secondly, in humans, the weights associated, the incoming and outgoing weights associated with neurons are not very synchronized, whereas in convolutional deep neural networks, particularly, you have tied weights, so to speak. That the kernel or the set of weights that is applied to the any particular spatial location in the image is the same. So there's a lot of a high degree of synchronization there. Secondly, fourthly, the receptive fields or the receptive fields of human or animal neurons are constrained in a way. They are rather smooth receptive fields. Usually they are Gabor filters or something similar. Whereas in DNNs can have arbitrary receptive fields. And then finally, human vision or animal vision is not as high resolution as DNN vision. DNNs see the whole image in full resolution at every particular spatial coordinate, whereas more than 90% of the visual field of animals and humans is very low resolution. And this is the point that we will be focusing on in this research. That the hypothesis that we are exploring is that the fact that human vision is very blurry and that we view the world at different resolutions allows us to become, or somehow makes us more robust. So as I mentioned, human vision is high resolution only at the point of fixation. So exactly where you're looking at, that's where human vision or your vision is high resolution. So you can test it out. You can focus on a word, and then maybe you can read the word next to it, like adjacent to it, but you cannot read words that are 2 or 3 words away, because our vision is very sharp only at in a very small area. That's and then further away from it, it gets really blurry, and we cannot make out a lot of details. We cannot even read things. And this phenomena is called foveation. Due to these constraints, researchers have found that humans rely on low frequency features of images such as shape, whereas DNNs who are not constrained in this way tend to rely on high frequency features such as textures. And it has also been found that adversarial attacks against deep neural networks tend to exploit this high frequency region of images by adding perturbations or adding noise into those high frequency components. That is why we do not perceive that noise, because it lies in an area that we do not give much importance to, in area of the frequency spectrum. But since the model gives importance to that high frequency region of the image, it gets fooled. And so to validate this hypothesis, we simulate foveation as a pre-processing step in CNNs and evaluate its impact on robustness. So I'll give you a bit of background on foveation. In our eyes, on the retina, that's the film that on which the image is formed, there are 2 types of photoreceptors. One of them are called cones. They are sensitive to color, and they are concentrated in the center of the retina, where you see the most high resolution. And then the second type of photoreceptors are called rods, and they are sensitive only to illumination. So, and these are not present in the center of the retina, but rather they are present in the peripheral regions. So these rods, they lead to grayscale vision because they're not sensitive to color. They are only sensitive to illumination, so it's like looking at things in grayscale or black and white. So as I said, cones are densely packed in the center of the retina. That's exactly where you is the point where you're fixating, or when you're looking at things. That's the center of your visual field. And then their density, this is represented by the blue line, their density exponentially falls off, and they are not as densely present in other places of the retina. Whereas the rods that are only sensitive to illumination, they are not present in the center of the retina, but they are present in the rest of the retina. So this leads to the fact that our vision has maximum fidelity, and also called by fidelity we mean highest resolution and highest color accuracy at the fovea, and the fovea is the center of the visual field, and it deteriorates very quickly in the periphery of the visual field. That's the off-center regions of the visual field. And so this graph shows the top line show how the accuracy or like the fidelity of color vision deteriorates, and this line shows how the fidelity of grayscale vision looks like. So this line represents the amount of detail captured by the rods. That's very little, whereas this line shows the amount of detail captured by the cone photoreceptors, that is the highest at the center of the visual field, and then it exponentially decays as you go into the periphery of the visual field. And because of this, the perceived image in the peripheral regions of the visual field is low resolution and appears desaturated in terms of color. It appears grayer. And so we designed this filter called R-blur that simulates foveation using adaptive blurring and desaturation. So starting with the image on the left, the red point being the fixation, where the model is fixating, we get the image on the right, in which that region is the one that has a high level of detail retained, whereas it gets progressively blurrier and grayer as you go further away from the fixation point. Now, to give an overview of what we do in this, how this filter works. First, it selects a fixation point, which is this red dot here. Then it adds Gaussian noise, and this is done because, as I mentioned earlier, the activations of biological neurons are stochastic. So to introduce the stochasticity in the neural network, we add Gaussian noise here. And then we split the image into color and grayscale channels, and this is to simulate the rods and cones. So the rod channel, as I mentioned, only perceives illumination, so it looks at the image in grayscale, whereas the cones perceive color. So this color image corresponds to what's seen by the cones. And then we perform adaptive blurring on these images. By adaptive blurring, we mean that the area near the fixation point, that's this nose of the cat here, is not as blurry as the regions further away from it. So these boxes represent different regions. The numbers here represent the strength of the blurring applied. So it gets progressively blurrier. And then we combine the gray and color channels into the final image. And so the result of combining these images together like this is that the regions in the periphery, like the regions further away from the fixation point, end up being a little grayer and more blurrier than the regions closer to the fixation point. Now, the first thing we talk about is how to select the fixation point. During training, we select random fixation points, and the idea behind this is that the model should learn to be able to classify an image regardless of wherever it appears in the visual field. So even if you see something towards the edge of your visual field or in the peripheral vision, humans tend to be able to classify them correctly into high-level classes, and we want the model to do the same. At evaluation time, we follow an approach from some existing literature in which we fixate on 5 fixation points, and that is top left, top right, center, bottom left, bottom right. We feed all these 5 images to the DNN and then obtain its logits or classification probabilities, which we then average to get the final output of the model, the final classification probabilities. This is not necessarily optimal. So currently we are developing methods to dynamically select fixation points based on the image, because that's how humans work. We look at a scene, we identify certain interesting points in the scene, and then we go and focus on them. So that's sort of ongoing work. The second thing here is computing eccentricity. Eccentricity basically means distance from the fixation point. Now, in opticians, or in the field of optics, this distance is measured as the radial distance or the Euclidean distance between any point on the image and the fixation point. Now, the consequence of that is that you get this type of area. So like all the fixation points in this light green area, all the pixels in the light green area have the same distance, and then the ones in this dark green area have the same distance, and so on, because you're measuring radial distances. Now, the consequence of this is that if we want to blur the light green region, we would have to extract a circular region from the image and apply the whatever amount of blurring we need to apply there. Extracting circular regions is a little inefficient because the images are rectangular images. They're organized as matrices, so you would have to do some masking and matrix operations to extract circular regions of the image. So to make things more efficient, we use a different distance matrix that's shown here, and the consequence of that is that we get square receptive fields. So basically all the so now we have these square regions in which the points have the same distance from the fixation point, and so now we can extract this green square or this dark green square simply by slicing into the image tensor. And that's very efficient because you don't need to do matrix multiplies or masking, etc. Now, as I mentioned earlier, at the fixation point or in the center of the visual field, our vision is the highest fidelity. So fidelity or acuity basically means the same thing. Acuity is a term they use in optics literature. Anyways, the fidelity or the resolution or the color accuracy of our vision is highest at the center of the visual field, and it decays exponentially as you go into the periphery. Now, this is a plot that I found from a paper, but we need to be able to estimate or have some equations to estimate it so that we can find we can determine what is the visual acuity for any particular pixel in the image. Now, to do that, we use these set of equations. I've put the details on the slide, but I don't think they're very important. They're just designed so that they match roughly the shape of these curves. Now, as you notice, the first image, this one, that's a half a curve. So over here we have the full curve because we're going over the entire image. Assuming that the fixation point is at this here, this is how the visual acuity of color vision or the cones decays as you go further away from the fixation point, and this is how the visual acuity or resolution of grayscale vision corresponding to the rod photoreceptors behaves over time. Now, as you noticed, that this is a continuous curve, and what that means is that each pixel will have a different visual acuity value. Now, what that means is that each pixel would have to be blurred with a different Gaussian kernel. So essentially, we would need as many Gaussian kernels as there are unique acuity values, and we have as many unique visual acuity values as we have pixels in an image, essentially, or pixels in one dimension of the image. And for normal images, that value can be quite large. So we would be having maybe like 200 different or 100 different Gaussian kernels being convolved over the image, and that is usually very inefficient. So to improve efficiency, we quantize this curve as this. It appears that I inverted the colors accidentally, but you see what's going on. So we quantize it into fixed bins so that instead of having 100 different kernels, we can use maybe 4, 5, or 6 kernels to blur the image. And so now we use this quantized estimate of visual acuity or visual fidelity to blur images. We take this image, this is an image which has some Gaussian noise added to it. We separate it into color and gray channels. We use the visual acuity estimate of the cones or the color vision. That's this curve to blur this image, and then we use the visual acuity estimate of the grayscale vision or the rods to blur this image. And then finally, we combine these two images in a pixel-wise combination, where the pixel-wise weighted combination, and the pixel weights are given by these graphs. So this graph spans the whole image essentially, and then in the regions further away from the fixation point, the weight of the color image decreases while the weight of the grayscale image increases. So that's why you get a grayer image further away from the fixation point. Now, to evaluate our approach, we use a variety of models and baseline. Our first baseline is a basic ResNet we are using ResNet 18 architecture for all our models. And this model just gets the clean image. It's trained on the clean images as is. So this is the normal baseline. Then we have our blur, in which we evaluate it by giving it images at 5 different fixation points, and then we average its outputs, as I mentioned earlier. We also compare against another biologically motivated approach, which we call R-warp. And the idea behind this approach is it deforms the images in sort of a fisheye filter, as you can see in these. And we use a similar approach in which we fixate on the 5 different fixation points, like the 4 corners and center, as we did for our blur, except we use this approach as a comparison. And then finally, we have an adversarially trained model. I introduced adversarial training in the beginning of my lecture, in which the model during training is given adversarially perturbed data. We use the EcoSet dataset to evaluate our models. The EcoSet dataset is a collection of 1.4 million images from 565 classes. And then we also use 2 subsets of it. EcoSet 10 has 10 of the 565 classes, and EcoSet 100 has 100 classes. Now, going on to results, our first result is that our blur improves empirical robustness. What we mean by empirical robustness is that we take a model, we use some adversarial attack to create, perturb the images, and then we compute its accuracy. So in this case, we use the auto-PGD attack, which is a state-of-the-art adversarial attack, to try and attack our models, and then we just measure accuracy. So this is accuracy on the EcoSet 100 dataset. This is on the EcoSet dataset. The first thing we notice is that the adversarial attack. Okay, sorry, I think I don't have the legend here, which is my bad. The blue one, the blue bar corresponds to the vanilla model. The orange bar corresponds to the R-warp approach. So this one, an existing approach from literature, which uses the fisheye filter. And then the green one corresponds to our approach, which is R-blur. And then the red one corresponds to adversarial training. Now what we notice right here is that the vanilla ResNet model, baseline model, is totally destroyed by the adversarial attack. Its accuracy is totally gone. It's getting 3% accuracy or 13% accuracy. It's practically not functional. The R-warp model, this one, does a little better. However, it doesn't do as well as R-blur. And as we increase the size of the perturbation, that's along the x-axis, R-blur is able to retain more accuracy compared to the vanilla ResNet and the R-warp. And it's significantly more robust than those models, even at relatively high levels of perturbation, where all the other, where R-warp and R-blur have almost 0 accuracy. R-blur has relatively higher accuracy, like 14% accuracy. Now, it is not as good as adversarial training, but that is to be expected, because as I mentioned, evaluating adversarial training with these type of attack is sort of like giving it the test paper before conducting the test, because during training it has seen images that have been perturbed with similar attack method, and then so it has learned to be robust to these. Whereas it is important to note that our blur has not seen any adversarially perturbed data during training. The robustness of our blur is sort of emergent. It has not learned. It's a consequence of imposing human priors or human constraints on the model. Now, auto-PGD is, as I mentioned, is an empirical attack because we conduct this attack and we get some accuracy. So it's an empirical evaluation, but it's not a formal guarantee. And by that, we mean that it's not guaranteed that if tomorrow someone comes up with a better adversarial attack under the same constraints, the model's accuracy will not fall. It doesn't provide any guarantee. But there's a way to arrive at certain guarantees. and that's called certifiability. So I have two definitions here. One is called certifiably correct at R, R being the perturbation size. What this means is that the model F, if the model classifies an example X certifiably at radius R, it means that it will correctly classify X 99.9% of the time under random perturbations having size at most R. So that's a formal guarantee that says if you add any form of noise having size R, size in terms of L2 norm, having L2 norm at most R, then 99% of the time the model will be able to correctly classify the input. And then the certified accuracy at R basically means what proportion of the test data is certifiably correct when perturbations having L2 norm at most R are added to the data. So to compute these metrics, compute the certified accuracy, we use an approach called randomized smoothing. And the idea there is we take an input, our image, we add 100,000 different noise samples from a Gaussian distribution having a particular standard deviation. And then we classify each of these 100,000 images with these different noise samples added to them. And then we conduct a hypothesis test. Particularly, we compute the binomial p-value to determine what is the maximum perturbation at which the model can classify the image in a certifiably correct manner. And what we find is that R blur is not just empirically robust, it's certifiably robust. And these plots on the x-axis is the size of the perturbation or the radius of the perturbation in L2 distance. Now the y-axis is the certified accuracy, and we are comparing this. We're comparing the R blur model with a model that we call G noise, and this is a model that's trained with Gaussian noise only. So basically, it's trained with the first two steps of R blur. That's you take an image, you add Gaussian noise to it, but there's no blurring involved. And we're comparing with this model because this is the model that was used in the prior literature, and it was shown to be certifiably robust. And what we see here is that at different radii, the accuracy of, or the certified accuracy of R blur is relatively high. However, the sigma over here, that corresponds to this sigma that is being used to compute the certified accuracy, whereas the sigma over here corresponds to the amount of noise that is added during training of the model. So both G noise and R blur use some amount of noise during training, and so the sigma corresponds to that. So what we see here is that even if we do not add any noise while training R blur, it still it has a high degree of certifiable robustness. Secondly, we find that at higher radii or larger radii, so over here this corresponds to a radius or the L2 norm of 0.5. At norm of 0.5, the G noise model has a higher certifiable robustness than the R blur model, which is the blue line. However, at a higher radius of 1, so when you're exposing the model to larger perturbations, we find that the R blur model ends up becoming more robust than the G noise model. So the G noise model is the red line, the R blur model is the blue line. So we find that even though both these models have the same amount of Gaussian noise added during training, R blur ends up being more robust to larger perturbation sizes, more certifiably robust to larger perturbation sizes than the G noise model. Now the third result we have is that R blur is also robust to common corruptions. Now these are not adversarial corruptions, so because as I mentioned earlier, we want our models to be robust to a variety of different types of perturbations, not just these small LP norm perturbation, but even larger ones that humans are robust to. And so we evaluated our models on 19 different corruptions. These are not adversarial attacks, these are just common corruptions like noise. Some of them are illustrated over here: noise, blurring, different weather effects, compression artifacts, etc. And we applied these corruptions at 5 different severity levels. And so again, the blue box corresponds to the vanilla ResNet. The orange one corresponds to R-warp, that's the fisheye model from prior work. Green corresponds to R-blur, and red corresponds to adversarial training. And what we see here is that at lower perturbations, R-blur is not as accurate as the other models. But if the severity of the corruption or the intensity of the corruptions is increased, R-blur progressively becomes much more accurate than all the other models. So this is a box and whisker plot. So the dash over here corresponds to the median, and the median accuracy is computed across all the different corruptions at each severity level. And we find that in both these cases, the R-blur has a higher median accuracy than all the models, and especially it is important to note over here, it has a higher median accuracy than the adversarially trained model. So this illustrates the point I made at the beginning of the presentation, that adversarial training tends to overfit to the particular type of noise being added during training. It tends not to generalize very well to other types of noise. And that's sort of a constraint or the limitation of adversarial training. And that's where biologically inspired models that try to emulate what's happening in the human or the animal visual system potentially have an advantage, because they're not tied into a particular definition of perturbation. Their robustness sort of generalizes to a wider variety of perturbations. A fourth result is that each component in R-blur, from the noise to the adaptive blurring to multiple fixation points being used during inference, all of them contribute to the robustness of the overall model. And that's shown over here. The blue bar corresponds to evaluation or like accuracy on clean data, and the green one corresponds to accuracy on adversarially perturbed data. And then this one is the R-blur with all the components intact, and then we remove one component one by one, and we see that none of these has the same accuracy as this one. So removing a component, it always reduces the robustness of the model. So that shows that all components of R-blur induce robustness in the model. Over here we isolated a few components. So this corresponds to only if we add Gaussian noise to the input and don't do any blurring. That is less robust than R-blur. If we do uniform Gaussian blurring, that is that we pick one Gaussian kernel and then apply it to the whole image, that doesn't perform as well as R-blur. And if we only make the image grayscale, that has absolutely no impact on robustness. The robustness is non-existent in that case. Now, a limitation of R-blur is that it reduces the clean accuracy of the model. And we see that on EcoSet 10, the accuracy drops from 93.8 to 87.9, from 87.4 on EcoSet 100 to 75, and then on the full EcoSet from 71 to 57. That is a limitation. But what we found was that the accuracy of R-blur depends on the fixation point selection. And as I alluded to earlier, predefined fixation points like we chose in our evaluation here may not necessarily be optimal. And to confirm that, what we did was we took, for each image, we divided it into 49 spots, and those are given by the grid on the images. And so for each image, we sampled 49 fixation points we used RBLUR to fixate at each of these 49 fixation points, pass the resulting image into the model, and obtain its prediction. And we see that for some images, the model is able to correctly classify at all fixation points. But for some images, for example, like this one and this one, okay, by the way, if the square is colored green, that means at that fixation point, or like when the model was fixating within that square, it was able to correctly classify the image. And when it's colored red, it means that when the model was fixating at that particular square, it was unable to correctly classify the image. So what we see is that most images are the model can correctly classify the image at any fixation point. However, there are some images like this one, maybe this one too, this one, in which only a few fixation points are such that the model can correctly classify the image at that point. If we pick any other fixation point, the model is unable to correctly classify the image. So that expresses the need that we need to develop methods of dynamically selecting fixation points so that we are able to predict, okay, for this image we need to fixate somewhere over here and not somewhere in the center or at the corner. Now, so we did an analysis and we considered the best case, and in that case we developed this oracle which looked at each of these 49 fixation points and picked the one at which the model is able to correctly classify the image. Now, granted, there are some images, although none of them are shown here, on which there is no fixation point at which the model correctly classifies it, but for most of them, there is at least one fixation point at which the model is able to correctly classify the image. And what we find is that if we pick this, if we use this oracle to find the correct fixation point in the image, our accuracy goes up significantly. So over here is the accuracy under the method that I presented, in which I have 5 predefined fixation points at the corners and at the center. We are getting 87% on EcoSet 10, but when we pick the optimal fixation point using the oracle, we go up to 93%. And this is the accuracy that the vanilla ResNet was getting. Same thing here. In EcoSet 100, we go from 75 to 85%. On EcoSet, we go from 57 to 69%. And these accuracy numbers, if I go back here, are pretty close to the ResNet baseline. So essentially, what this means is that if we are able, or in the best case scenario, when we are able to correctly pick the fixation points, we are losing almost no accuracy, but gaining a significant amount of robustness. And finding methods to do this automatically are part of our ongoing work. Hopefully we'll have more results in a few weeks. Now with that, I'll conclude. In conclusion, I presented RBLUR, which is a method of simulating foveation by adaptive blurring and desaturation. And then we have shown that using RBLUR or integrating it with CNNs makes the CNNs more robust without the need of training the models on any adversarially perturbed data using adversarial training or any such like. We also show that the robustness of RBLUR generalizes to different types of perturbation, not just small norm adversarial attacks. And this indicates the promise of biologically motivated approaches to model design, especially with regards to improving robustness. We've also shown that predefined fixation as a limitation, that the predefined fixation points negatively impact the clean accuracy of RBLUR, but this loss in accuracy can be mitigated by better methods of choosing the fixation point. That I'll end my talk, and I can take any questions if there are.
Thank you very much, Ahmed. The talk is really great. There are many questions on the chat box. Can you read it one by one to answer it?
Let me see. Okay, I'll go with this first question from Salah, that is asking if there is any gradient masking happening in our method. And it's a good question that you ask. And to answer that, I'll point you to this result. That's specifically why we conducted this experiment with certifiable robustness, because certifiable robustness is is not a gradient-based situation. It's not a gradient-based method of evaluating robustness. It doesn't use any gradients, and so it's certifiable robustness is backed by formal provable guarantees. So, and if you notice, the accuracy that we get under certifiable robustness is similar to the accuracy we get under empirical evaluations. So, which means that that the accuracy we see over here is provably the accuracy we are going to get when our blur is subjected to any perturbation having the radius that is on the x-axis. So that sort of precludes the need to run auto attack, etc. Because as you know, running auto attack requires a lot of time. Even on simple models, running auto attack on maybe like 500 or 1000 samples takes like several hours. But this is a stronger, like certifiable robustness is a stronger result because it is a provable result, and auto attack is not provable.
I see. Hope your answer can satisfy Salah. There are following questions.
Okay. Then the second question is, have you used non-PGD adversarial attack? I have not, but again, we use the certifiable robustness result as a way to encapsulate other types of attacks, like which are done using different algorithms, because the result from certifiable robustness is independent of any attack algorithm, as long as it tells you like at this for this size of perturbations, this is the accuracy you are going to get. Now I agree with the point that perceptual adversarial attacks that do different types of transformations that are not necessarily norm-bounded may induce different results that are not included within certifiable robustness, and that's a good evaluation that we would consider doing in the future. And I thank you for raising that point. Next question. I think it's considered. What fixation selection would you like to use? Are you considering the real gaze one? And are you planning to do any wet experiments? It's a good point that you bring up. So we tried using some real gaze data. It's not really exactly gaze data, but it's a data set. It's called ClickMe. You can look it up, in which the researchers have enlisted a group of participants, and they had them select regions of the image they consider important. Now the thing is that those regions are not the regions that the model necessarily considers to be important as well. So in my opinion, a fixation strategy would be one that uses them or tries to learn the model's own preferences. So for example, in these images here, you would want to learn a model that is trained on the classification model itself in a way. So it learns to model a particular model's preferences for regions, and then sort of on unseen images predict, okay, the model is likely to like this particular region and is likely to correctly classify in that area. So we are doing certain experiments in which we're trying to train a fixation prediction network on a pre-trained classification model, but we're having certain issues with the convergence and training that we're trying to iron out before publishing it. But that's a good point. And as regards to conducting wet experiments, I'm not sure we would do that. There are certain, as I mentioned, like the ClickMe dataset, there is certain data regarding that. So maybe you'll probably use that, because in our lab we currently don't have the resources to enlist a large population and do those experiments.
Sorry, may I just add one more comment?
Sure.
So basically, actually, we have collected this data set, the gaze data set, because we are focusing on doing the gaze research. We have collected a real human gaze data set. So I'm thinking maybe this is published in last year's ECCV. Maybe you can use them to like do the fix selection, because the so actually, you know, the case selection, the case estimation has been a well-studied research. Yeah, so basically, like what you are saying, like for example, the treasury and the things they have been, like, how to say, has been well studied actually. So we are just like the one part in it to provide the latest, like the real human case data set.
Okay, that's great. I'll definitely look at that. If you could share a link or point to that paper.
I will send you a follow-up mail. And for the second one, I'm also very interested in, are you planning to do some real wet experiment? Because we as a RICAN, so we belong to RICAN, so we are actually a comprehensive, like the institutes across the whole Japan. So we actually can do the experiment on the mouse. So are you planning to do, so for example, we can just do the experiment on mouse, and we just put some electronic into the mouse retina to measure the response. So do you have any plan to do some like the wet experiment and to real test to test what you're finding in the real mouse?
Unfortunately, we can't do it because like the group I'm part of, it's mostly a machine learning group. We don't have any expertise with wet experiments. But I would really be interested in looking at any data that you have from the wet experiments, and let's see if that corresponds to any results that we have.
Okay, that would be great. I think that we can just discuss more in the follow-up mail.
Yeah, that would be perfect. I look forward to talking to you.
Okay, thank you.
You're welcome. How does human or animal select fixation points? Possibly, does the analysis help improve results? So that ties in with the last question. And essentially, humans have certain metrics of what they find interesting and what parts of the image they find useful, and that would be shown in data that, as Lynn mentioned, that's collected on real humans. We have not done those studies, so we don't have any strong opinions about that. So I think those are all the questions in the chat. If I missed any, just please.
Thank you very much. The talk is indeed very interesting. We hope when you have time, please visit Japan, Tokyo. Our center is in the center of the Tokyo, is near Zenza. Very, very nice place.
Okay, I'll be sure to visit if I come to Japan.
Sure. Great.
Thank you for having me.
This is the end of today's seminar. Thanks again for Ahmed's great talk.
Thank you.
Bye-bye.
Bye.